Well, here's the attendance form. Go ahead and do that. Again, it's also in the chat. Let me know if it doesn't work. I'll fix it. Yeah, we're doing unit 4 today. Oh, yeah, I also have last week's responses. It looks like Saturn and Jupiter are tied for first. I guess the bigger planets are more impressive. I don't know. Yeah. I guess I'd expect this. Yeah. I didn't put Pluto as an option, actually. What the... someone put Pluto. That's cool. Okay. Any questions on the logistics? No? Okay. Let me switch over. Oh, this is a wrong slide. No, I'm spoiling it. No, okay. All right. Computer vision and convolutional neural networks. So, yeah, let's just, we'll start with the motivation. What do we mean by these big words? We'll break it down. And hopefully by the end of this, you'll know what a convolution is and how this whole image kind of works. Because I don't even understand, the exact specifics everywhere. But, once you know, what's kind of happening, you let the computers do the rest, and then it'll work. Yeah. Okay. So remember our deep neural network that Varun went over. It kind of looked like this, right? You get this input layer. You do a bunch of weights, which is just a dot product or it's a matrix multiply, which is these lines, right? And then you get some other result, and then you do another matrix multiply, which are the lines, after applying some softmax, some activation function to introduce nonlinearity. And then you get your output, and that's your answer. And then you just backprop on the weights, and it just works. How does this fail with images? Or it does fail. And why is that? So this is kind of how it sees images, right? It stretches it out into this one-dimensional input layer. So I want you all to turn and talk and try to guess what each of these lines are. I'll refer to them 1, 2, 3. Yeah. Ask each other, just guess what it is based off the color. Maybe. What do you think? I gave you some questions to start. Is it a living thing? Is it a landscape? Yeah, you're not supposed to know. Yeah, that's the point. Yeah. Okay. Yeah. Okay, so, anyone want to share out? By the way, I didn't make it clear, but each line is a different image. So yeah, you were saying seal? Which one?
Middle.
The middle? Why do you think that?
I don't know, it looks like a nose.
Okay. Yeah, the shape of a rounded thing, because it's sliced up, right? Yeah, but the whole point of this was you really can't tell, you know. Here or actually, I want you guys to vote. Do you think the first one's a living thing? Thumbs up if you think it is. Thumbs down if you think it isn't. Yeah, 50-50 from what I see. Yeah, I'll just show the answers. First one was a turtle emoji combined with a thumbs up that my phone can do because Google's weird. Selfie, and yeah, a landscape. So, did anyone get that? Yeah, okay. That's what I thought. So that's the issue, right? This is what the computers see, and this is an iPhone selfie that I took on my roommates because I don't have an iPhone. But it's huge, right? 3,000 by 2,000 pixels, and each one has an RGB value. This is if you were to stretch it out and put that in that first, that first thing, you would need 3,000 times 2,000 times 3 of these circles, right? And that's just hard to do. And another thing is, if you slightly shift an image, it's called translational invariance, the numbers immediately don't line up, right? So this is just that. What the hell? This array is just this one flattened out, and then the bottom one is the one on the, I'm so bad with on the right. And you can see the numbers aren't matching up. So this model would think these two are completely different. It's the inputs are completely different. These two are completely different. So it will think of them. It won't realize oh, this is just the same image shifted, which we can clearly see just by looking at this. So we need some sort of way to look at things that are close without actually just going one for one, doing the entire matrix multiplication. And so what else did I say here? Yeah, temporal relationships. Yeah, I guess the answer is this: convolutions. So what is a convolution? It's everything good. It's like a pattern extractor is how I like to think about it. It is just a mathematical process, kind of like you can do a dot product with two vectors. You can do a convolution with two matrices, and the math involved is like predefined. Like there's just a set of steps, and I will go through the steps with these exact two matrices. But you can think of, I think it helps to think of it as a sliding window. Please stop me if you have questions. This was super confusing the first time I looked at it. So I'm just going to go into what a convolution is, but any questions about the previous stuff so far? Yeah. What is a kernel? Oh yeah, so that's like another matrix basically, which is usually much smaller than what you're doing the convolution on. I'll go through some examples, but in this case you can think of it as like the pattern that you're applying to this image or matrix. Does that make sense? A bit more? Okay. That was a great question though. Yeah.
What are those patterns supposed to be?
We'll get into some examples, but some just things off the top of my head that they can do is just with a kernel, or like just doing a convolution with a kernel and an image, you can do like blurring, sharpening, edge detection, and we'll get into that. We'll see some examples of those. You just have to trust me at this part, I guess. Yeah. But we'll go into what the math involved is, because like I said, it's kind of like a dot product, but it has its own rules. So, okay. Basically, we took the kernel, right, like the 0.2, 0.5, 0.2, that kernel, and we put it on top of where it fits, like in the top left of the image. And then we're going to multiply the two numbers like this way that are here. So then 3 times 0.2, 7 times 0.5, 9.2, and just like that. And then we're going to multiply each one in each cell and then add this matrix up. And then the kernel is here right now, so then it'll go into the top left of our output. Yeah.
How did you get like the specific numbers for the kernel again?
Oh, again, just random. This kernel is purely just random. You will see how we can like put specific numbers into the kernel to get cool stuff like later. Okay. But right now, just think of it as you got two matrices. What's a convolution? That's what I'm going over. Don't worry about the actual numbers. Right now, it kind of doesn't mean anything. But yeah, because if we did like simpler numbers, I feel like the actual math involved. Because there are some kernels where every value is like the same thing, like 1/2, 1/2, 1/2, 1/2. So yeah, then it's like then the math gets kind of easy, I guess. I wanted to complicate it a bit. So yeah, we'll multiply it, add it, and put it in this cell. This is one step of a convolution. Does that make sense? Okay. Then we're gonna repeat it. We're gonna shift the kernel one spot over, and then put the output one spot over. And if you notice, the output size is like the perfect size for how many times you can slide this around, right? Because then you can go down one row and back to the left, and then push it aside, and then go down one more and push it aside. That is, and I'm rounding at the end, by the way. That's the result of the convolution between those two matrices that we saw earlier. Then this is what a convolution is. Does this make sense? Any questions? Because we're going to build off of it from here. Okay, but feel free to stop me if you want me to come back to this image, because I think it's really helpful. Okay, because now we're getting into how that convolution will work in our neural network. We're going to make a layer. So before, like, we had those hidden layers, right? And that was just the result of a matrix multiplication with the weights, which are the lines in that image, and then you get one big hidden layer of just numbers. And you applied the activation function, right? But this time the layer will have a kernel, which again, I'll talk about what we put in that kernel, but then it'll kind of like extract features through it, and it can like that temporal locality that we wanted before will now be we'll be able to do that. So this is like one example. The depth is 3 because again, in color image you have RGB values. So you'll slide this kernel along the whole thing and then you'll get a slightly smaller output. And that's the example of one convolutional layer. But now we'll get into understanding kernels. So if we took, for every pixel value of this turtle, if we put this kernel, did that multiplication we were talking about, what, and we're going to do 1/6 on this side, positive 1/6 on this side, negative 1/6 on that side, and a 0 in the middle. I want you guys to think about what could possibly happen. Like, think of when that product and the sum would be like positive, when would it be negative, when would it just be 0? Because like, think about doing it here in this white space. White is basically like 1 in RGB values, or like 255, and 0 is black. So it would just be like 1 times that, but then that side's negative, so it would just sum up to 0, right? So turn and talk, try to think about what this could possibly, like, what feature or pattern is this extracting from the turtle? Or is it just no idea? Okay, who has no idea? Raise your hand if you really have no clue. Okay. So the people not raising their hand have some idea?
I'm just a little bit worried about the color coding, especially on base color.
What do you mean by that?
Well, because you said earlier you're sliding the kernel.
Yeah.
Like that.
Yeah, you'll go across. Yeah.
This whole like image with one matrix.
Yep.
But it would still like go for 0 for like any other way.
What do you? It'll.
Like any like negatives.
Right. Anything with the same value, because it would just cancel out, right?
Yeah.
The 1/6 and the negative 1/6.
And then for like the turtle itself, I think the
Yeah.
color would be
Yeah.
because of the way the sign up plus the layers.
Yeah, maybe. I mean, it might be easier to see, but yeah. Okay. Okay. I like hearing conversation again, even if it's off topic. That's good to hear. So let's think about this. So again, in the white space, the negative 1/6 and the positive 1/6 like will cancel out because white is 1. It's the same value. But let's say we're coming up to this edge, like the window is sliding, and the 1/6 are on this green, but the negative 1/6 are on the green, but the positives are on the white. You now have a difference in value. But then when you're back fully in the green, it all sums up to 0 again. And yeah, basically the answer is vertical edge detection. So it's really hard to see, sadly. Can you guys see it, kind of? You basically get, like, any time there's a change in color vertically in this image. And it's like, that's what these little gray lines are. Again, kind of hard to see. But yeah, okay. We're gonna experiment a bit more now. So okay. Hopefully not too much got lost. Okay. When you actually do the convolutional neural network for this week's project, this is kind of abstracted in a similar way how like the actual, if you did the deep neural network, the actual like, what's the word, the dot products, the multiplications, you don't actually do. You just call like x dot hidden layer, x dot feed forward, x dot like softmax, or whatever your functions are. But this, I'll actually have the convolutions. So yeah, run this thing at the top. Raise your hand if it doesn't work, because it should work. These are just packages. Image IO is to import the image. PLT is to show the image and plot it. NumPy is so we can read the images as a matrix and do our cool multiplications. This was a cool thing Chayton showed me yesterday, which is like a loading bar, which we'll see later, which you can just throw on a for loop in Python. I think it's super cool, but yeah, not really necessary. So we'll also need to run this. This was just, it just opens a file. This is the actual convolution method that I wrote. If you don't understand everything, don't worry about it, but it just takes an image and a kernel and runs the convolution and returns it as a result. If if you have questions about this, let me know. It divides by 255 because we want to go from the integers to the floats. If you have an image as a matrix, as an integer, the pixels are between 0 and 225. I think I wrote that here, yeah. But if it's a float, they write it between 0 and 1 as a float, where 1 is white, 0 is black, yeah. So I'm going to open the image. Okay. So it removed the image for some reason. I don't know why it does this, but here's what you have to do. So once you download it, just take the image, drag it over in here. Yeah, it'll say, okay, yeah, it doesn't save, but it's there. And then you should be able to run this. You can put your own image in, just make sure this string name matches that. And if it doesn't work, let me know, or we can just follow along here. And then we can look at the image now. The background turned green in this one. PNG is weird. There's like 4 values to it. But let's look at one of these RGB pixels. So I just chose index 255 out of 255. That's like somewhere here. So I guess it's one of the green. And it looks like this. A lot of red, more green, not much blue. Right? So this is how it stores the pixels. If we print out the whole thing, the whole matrix. Oh wow. Okay, I didn't expect it to. I didn't want to look at it like an image. Okay. Well, yeah. That's impressive. But that's what the variable turtle now stores. So this is the kernel that we just looked at. I made it half instead of sixth because you can kind of see it more. Then if we run the convolve method, there's the cool loading bar I was talking about. You can see the vertical edges, right? So what I want you guys to do or think about is how can we change, all you need to do is just change this kernel, but how can we change this to detect horizontal edges? I'll give you guys 5 minutes, like turn and talk or code. Feel free to ask me questions, raise your hands. Yeah, till 52. Okay, so it seems, okay, raise your hand if you got it to work or think you got it to work. Okay, decent amount of you. If you didn't, that's totally fine. I'll go over it. But I did want to bring up one thing. I had a good question asked. It's like, I mentioned the output size would change, but this turtle and this turtle like look like the same size. So did it? And yes, it did. The new size is this, where H is the image height and width, and KH and KW is the kernel's height and width. So it's the image's height minus the kernel's height plus 1. So we're using a 3x3 kernel, so the height and width got shortened by exactly 2 pixels. So it's very similar, and when, I think the dimension was like 500, it's hard to see for us when it's that little bit of a change. Actually, I was thinking about it. Another thing we could probably do is if we make this the absolute value, you would see both the negative and positive difference in this. Let me just run that. Yeah, maybe I should. Or actually, that's just all edge detection. That's boring. Yeah, let me go back. Okay, so as some of you have done already, I'll go over the answer. If this is vertical, horizontal would be kind of literally rotating this. So we want positive 1/2, or you can do it all negative on the top as long as you're consistent. Zeros across the middle, and then negative 1/2 on the bottom, like that. And then when you show this, you will see the horizontal edges, just like that. Any question? Yeah.
How much do the numbers matter in if you had the same thing?
Yeah.
Instead it was 0.2, 0.2, 0.2.
Here, I'll do one.
Negative 0.2.
Yeah.
Is it just the vibrancy, the actual edges?
Yeah.
The same edges?
Yeah, that's exactly it. It's like the strength. So I reduced this to 1/6 now, and when it runs, you can barely see it, right? Yeah. So this is actually what I had earlier, and then Chayton was like, why not do 1/2? And so, yeah. Yeah, good question. Anything else regarding that? We'll be done with you can mess around with this code all you want. Again, let me know if you have questions. You can make the kernel like 5 by 5, do some cool things. We could try the edge detection where like 8 in the middle, -1s on the outside. What I did want to try actually, okay, bear with me while I code this up really quick, is a sharpening kernel where it looks exactly like edge detection, but instead of the sum being 0 if everything's the same, you have it be 1. So like things that are similar still show up. So this would be 9. So if the underneath image is like the same value and all the pixels say 1, the convolution at that patch would be 1. So then this is technically sharpening. I don't know how well it will look though. Oh yeah, have you guys messed with the sharpening filter on your phone before? Kind of looks like that after you do it compared to the original. Yeah, I don't know. I think this stuff's super cool. Okay. Again, feel free to stop me for questions, but I will continue with this if not. So yeah, so here are some more. This is straight from Wikipedia. If you just go to convolutional kernel or something, I forget the exact thing, but something related. Other common things are blur. Where's blur? Yeah, blur on that side. So if you just do like 1/9 on all the values, you get it's called box blur. And then there's the Gaussian blur where the distribution of the values in the matrix is distributed like the normal distribution, which is what that is. You might have seen these terms in Photoshop. I have, and I thought it was super cool. Any questions about this? Does this answer you guys' questions about like what to put in the kernels? Does this kind of make more sense? Like these are the features we extract. Okay. But what kernel should we use for our neural network, right? And like what size? It depends. So you can choose the size. It's usually square though. I don't know a case when it wouldn't be square. There might be cases for that. You choose the step. So like we had a step or a stride of 1, right? We slided it 1 at a time. But sometimes, say you have a 5 by 5 kernel and your step is 3. I don't know. You can just choose to do that. These are hyperparameters, right? The padding, which someone brought up earlier, like you lose information on the edges with kernels. I'll show this better later, but it's like extra, literally just 0 values you add on the outside of your image so that your kernel, or when you do the convolution, the resulting size doesn't get shortened or doesn't change too much, or to not lose information on the edges. It helps with all of those things. But what to put in the kernel, you just randomize it. It's the same as like the matrices, the lines in the deep neural networks, because we don't know what to put, right? Like how am I like it is hard to know. Like say we're trying to classify like a coffee table or the numbers digits, right? Like what's the best kernel to put to recognize the difference between an 8 or a 9, right? It's hard to know, but you just randomize it, you do backprop on it, and then it just you calculate the loss, and then do backprop to make sure the loss gets less, and then it just kind of works. That's what's so cool about it. Any questions about that? Okay. Yeah, there is relations to a brain. There's more on this next week. So, and again, I'm no expert in this, but I'm sure Chayton can answer questions if you have any. And this link is super cool. And I'll link this into the mega slide deck. But there are these simple cells and complex cells in the brain, which are very similar to what we're trying to do here. And I think that's how they initially like tried this idea of a convolutional neural network, is they were looking at the brain and they realized, oh, the brain is somehow, there's some cells that look at exactly where things are in your vision, like position wise, but there's some that just look at relativity, or it's a neuron that fires based off of other neurons firing, like kind of like the pattern, right? I think the website had a really cool image, but I don't know if it was this. Yeah, I mean, there's a lot of cool stuff here. I don't understand much of this. It's out of my domain, but feel free to read up on it if you're interested. Yeah, what's going on here? Okay. yeah, again, more next week. It's called Unit 5, but we might actually do Unit 12. It's all related though. Yeah, that'll be cool. Yeah, here are the definitions. So I'll kind of run through it because we've talked about it, but please stop me if I'm going too fast. So kernel, it's the matrix that extracts the features from the input matrix. The size is the dimensions, and again, usually in a convolutional neural network, it's square, so 3 by 3 and 5 by 5, and it's usually odd as well. I don't know. There's probably good reasons for it that I don't know, but yeah, that's just what I usually see. And then number of input channels. So a channel is like your depth. Usually it's 3 for RGB, sometimes 4 for like A, like opacity, RGBA, 1 for black and white images. And then a filter is one group of kernels that then output to a single channel. So in this case, it's you'll end up getting one value per RGB pixel, or per RGB kernel, I guess. And again, all of these kernels will be randomized, done backpropped on, so each channel as well, like red, green, blue, can have their own kernels, which is really cool and adds more depth. And if you have multiple filters, you get 2 output channels in your convolution. Yeah, and that's the number of output channels. The depth of the output matrix here, it's 2 based on the amount of filters you have. Yeah, okay. Number of filters, number of output channels, which is the depth of the output matrix. Right, this gets into stride and padding a little more specific. So yeah, I guess just take a look at the GIF. But this one is a stride of 1, right? It starts here, slides over 1, goes down, slides over 1. This one, the matrix is wider by 1 and deeper by 1, but it's the same amount because we're not going 2 by 2 in the X and Y every time. Padding, as we were talking about earlier, you just add zeros to the edges, and then when you convolve with those zeros, they don't really like take away anything. It's just the edge, right? Any questions on this GIF? Cool. Yeah, this is like a calculation for the output size. Before, what I was showing you was if you take the padding out, then the times 2, and you take the stride out, that's exactly what I was showing earlier. It's the input size minus kernel size plus 1. But then if you add the padding, we do times 2 because, go back, if you pad by 1, it adds 1 to both sides, right? Because you're going around the whole edge. So we multiply by 2 for that extra size, and then divide by the stride because that's how many times your kernel will actually multiply into it. Should I leave it here? Any questions on this? Cool. Pooling. This is another important term that you see in convolutional neural networks. It's a layer that basically, when looking in a certain area, so a very common thing is max pooling. It'll just take the maximum value, and it helps with reducing like the dimensions instead of a huge size. If like take my iPhone selfie, right? If I just pooled through the images to like what it was 3,000 by 2,000 to like if I pooled like 2 by 2, then it would be 1.5 thousand by 1,000. So like half the size, and you'll basically have the same information stored. There's also average pooling, where you take the average of each area, and then that's your output. And there's more types as well. Any questions on pooling? I'll try to show a more in-depth example. Yeah, downsamples the data, prevents overfitting. Oh yeah, it helps with the transitional invariance, because if everything is shifted by, say, 1 pixel in this case, it won't change the pool because we're just taking the max out of it anyways. So if the max shifted over 1, it's still the max in that area. And yeah, if it reduces the size, it reduces computation time. And that's everything you need to know for a convolutional neural network. And it is a lot. So again, let me know if you have questions, but I'll go through kind of like one, I don't know, process. So again, the amount of layers you have though, and how big your kernel is, how big your max pooling is, what else is there? Like the padding, like this is all just your choice. Like this could literally, we could just have one of these and then just go straight to the output. But the more you do, the more activation functions you add in between each one, there's more weights to train, right? It's kind of similar to the deep neural network. So in this case, 5x5 kernel does a convolution. It seems this is just a random image, but yeah, it's doing it on the handwriting data set that we already looked at. And then you'll do kernels of the output of the previous kernel with, or sorry, this one's a max pool, and then you'll do a kernel of that, and then you'll max pool that, and then at the end they have like an activation function, and then, but basically the end goal is still to get, like, in this case with the digits, that 10, the vector of like 10 items, which each represent 0 through 9. And then you train it so that it matches the number you want. So at the end, we hope to see the number where 2 is, that red dot, to be really large compared to the others. And if it's not, it wouldn't be at the start, right? It'll be complete gibberish. But then you calculate the loss, do backprop, and then you do that a bunch of times, and then the kernels get better, the max pooling is better, or the max pooling is procedural. The kernels get more fine-tuned, those are our weights, and then it just works. Any questions about that? Because it's a lot. No, there's no way I explained that really well. But if questions come up, let me know. There's also, yeah, this one's cool. There's a visual, like, there's this site that kind of shows you convolutions, like an example. I guess the coffee cup's a good one. So this is like a classifier between, what do we have here? It might be hard to read, but we got like, it'll classify between a lifeboat, a ladybug, pizza, bell pepper, school bus, koala, espresso, red panda, orange, and a sports car. My bad. Let's do the espresso because it's cool. So here at the first layer, we got our 3 input channels, and this is an actual trained convolutional neural network. And again, once you train it, then you just input it, do the kernels, do the procedures, and then the output, it just works, right? Or it works really well. So take this for example. It takes a kernel for each 3 layers, and you can literally, if you hover over it, I think you can see the value of, you can see the values that they have in the kernel. Like, it's really small, sorry. Oh, I can blow it up. Like, this is the kernel value, 0.9, 0.09, 0.01, 0.08 for this one step, okay? And then it'll sum up between each channel, and then you get this. And then it does, what does it do after that? Okay, it does ReLU, so it does an activation function. And then from here, you do that with all the channels and all those, and then you do a whole bunch more, another convolution. And then you do another activation, and then you do max pooling. Here's max pooling, which like reduces the size of it. If you see, like, this one's more pixelated, so that's max pooling, but you kind of get the same idea, right? The same features. And then another convolution, and then by the end, if we look at espresso, I think they do sigmoid over it. Whoa. Okay, I would recommend messing around with this site if you're confused. I think it's really useful. It might help when you're also making your own neural network for the project, because it's like, what you really have to keep track of with this is, when you do a convolution, what's the output size? Like, like, how big is the matrix still? And then just keep filtering it down until you get to your final n amount of classifiers. Yeah. Any questions? And I think we'll be having you do classifying this data set, which just has a bunch of images of these like 10 classes. Looks like we got dogs, birds, planes, cats. Yeah. Yeah. Anything else? Yeah, I think that's all I had for today. Any final questions? Yeah.
I guess, like, when you train a convolutional neural network on like an image, does the kernel like change as that's doing? Like, is it updated with parameters, or
when you train, like, how does the kernel update? So in the process of doing the actual convolution, nothing gets updated, right? You just have your set kernel, you get your output, and you'll get that vector of, say we're classifying digits, you'll get your vector of like length 10. And then you'll look at what it should have been, right? Because you'll have your labels if in training. So you'll know like, okay, this is supposed to be a 2, but say like 9, it thinks it's a 9. And then you'll calculate the loss, right? The difference between the two. And then you'll do back prop. So back prop kind of, it lets you know which, it'll go to kind of each multiplication done in all those convolutions and be like, you should have gone in this direction, like nudge you in that direction. And it'll do it to every single weight. And you just keep doing that a bunch of times for all the numbers, and that's so it's the back prop that does it.
So would you say, like, is it possible that like a normal like deep neural network would have the same like layer sizes as a convolutional one, or would that like never be the case?
You can definitely make one like with the same sizes. Again, the sizes of the layers are hyperparameters, they're your choice. And I think the start of the technical project will actually have you do a deep neural network on, I think, the Cypher data set, or it was either the handwriting one, but I don't think it was that one. And you will, like, we expect to see a very low score. You'll get like 50% accuracy, which is still pretty cool, I guess, for, again, it's just dot products, right? But this one will be much, much higher accuracy. I think 85 plus, if I remember right. Yeah. Does that answer that? Yeah. Any other questions? Yeah.
So is it correct that after the last quick layer, it flattens it and then it passes it into a neural network exactly the same way as before?
Yeah, I believe so. Yeah, this one has it. Yeah, so it'll flatten it. Yeah, the final layer has to, because you have to get it to your flattened like n classes vector. In this case, it's classes as well. Yeah, and then again, this website, hover over. I don't know how this works, but like this is how it flattens it, I guess. Can I see? Okay, I can only see the top and bottom one for some reason, but like each pixel, I don't know. It must be hard to see, but like that value in that flattened vector is that one pixel in that image. Yeah, and then as you go down, it goes down through the images.
So basically, by doing convolutions, you're trying to get the neural network and input that it would better understand.
Yeah, and it's kind of like deep neural networks where we don't fully know what it's like thinking. If we had to, like, we can guess, and we have pretty good guesses, but we don't know the exact things. We can totally look at the weights, like I said, but it's like, what is it actually doing? Like maybe, like it looks like, oh, this one tries to extract the coffee, like the oval in the cup, but then I don't know, if you go to like this, I don't know, the school bus, like what's it extracting here? Something. Like the headlights, we don't know. But the way I like to think about it is it learns to figure out these features, just different features, patterns. I like the word patterns for this. It picks it out and then gets it into some output. And that's it, yeah.
Can you explain again what a pooling layer is?
Yeah. I think this does a good example. So it'll just, so this is max pooling. So it'll take, okay, this is like one, it'll slide this 2x2 window throughout the whole thing, but at one step, say this step, it'll look at the pixel values of each one and just take the maximum number of it. And it'll just take that one pixel there. So it basically divides the whole size by 2, right? 60 by 60 to 30 by 30 by just taking the maximum value at each 2x2 location. So it just like shrinks it while still keeping the important stuff, if that makes sense. Yeah. And then I can show it. Yeah, it does it through every single 2x2 in order. So like this one corresponds to the 2x2 matrix in that input. Does that make sense? Cool. Okay, if you have more questions, come ask me right after. We're at the end. Yep. Thanks for coming. Do the synthesis questions on Tuesday. Project on Thursday. I'll send reminders as usual. Hope to see you next week. Thank you.